Be careful watching.
And now that is in perpetuity on the video. That's the beginning of the video. All right, you just blew my opening statement there. So far, we have, everything we've differentiated has been with respect to X or with respect to whatever the independent variable is. And we really didn't know what that X stood for because we haven't done very many word problems. Well, your two big sections of word problems in Cal 1 are 3.7 and I think it's either 4.7 or 4.8. The two big kinds of word problems are related rates, which is 3.7, and then optimization problems, which are somewhere in chapter 4. But in related rates, we're talking about quantities that depend on time. And on page 187 in the book, you have a chart I like because it gives some examples of quantities that depend on time. It gives you the verbal statement and then how we'll translate it to a mathematical model. We're going to be coming up with an equation of quantities that depend on time and then differentiating with respect to time. We'll have dx over dt or dv over dt. For example, the first one, the velocity of a car after traveling for 1 hour is 50 miles an hour. If x is the distance traveled, then dx over dt, think about what the units would be there. That x represents miles and that t represents hour. So dx over dt is miles per hour. And the symbol you'll use for that 50 is dx over dt is 50 miles an hour when time equals 1. In 1 hour, the velocity was dx over dt, the velocity was 50. The second example, water is being pumped into a swimming pool at a rate of 10 cubic meters per hour. If your units are cubed, what do you know that that's a measure of? That's volume. All right, so that's a change in volume per hour. So the symbol we'll use for that 10 is dV over dt. The change in volume with respect to time is 10 cubic meters per hour. The gear is revolving at a rate of 25 revolutions per minute, and 1 revolution is 2 pi radians. If theta is the angle of revolution, then we're being given that 25 is revolutions per minute. So the symbol we'll use for that revolutions per minute is d theta over dt, a change in theta with respect to time. And the last one, a population of bacteria is increasing at a rate of 2,000 per hour. If x is the number of bacteria in the population, then dx over dt, that'll be the change in population per hour is 2,000. So a lot of this section is going to be using the right notation. And that's why I've been a stickler on notation, trying to get you to use the right notation all semester. It's going to be critically important that you do that. You have everything labeled correctly when you're doing word problems. So we start out with some easy ones today. Let's see, through with that. Here we go. Get that where you can see it better. All right. Things that depend on time. Assume that x and y are both differentiable functions of time, such that x squared plus y squared is 25. Well, the graph of x squared plus y squared is 25 is a circle with center 0, 0 and radius 5. So I drew that circle for you. And I want you to imagine a marble rolling around that circle, and the ordered pair where that marble is at any given moment depends on how long it's been rolling. You may start it right here at 0.10 and find out where it's going to be in 3 seconds, in 5 seconds, in 9 seconds. All right, we have an equation that relates X and Y, where X and Y both depend on time. So we want to differentiate both sides with respect to time. And just like implicit differentiation, anytime we were differentiating something with a Y in it, we said Y is some ugly that we don't know. So part of the derivative has to be ugly prime or Y prime. Well, here we're differentiating things that depend on time. So whenever we differentiate a variable, we have to have dx over dt, or the derivative of that variable, as part of the derivative. I didn't say that well. The derivative of that variable with respect to time. For example, when we differentiate both sides with respect to time, the derivative of x squared is 2x, and then because x is some function of time, we have to have dx over dt. It's not sufficient just to say x prime. We need to show what we're differentiating with respect to. Second term, the derivative of y with respect to t would be 2y, and then the derivative of y with respect to time. Because x is some quantity that depends on time, and y is some quantity that depends on time. The derivative of the right-hand side with respect to anything is just 0. So that's the derivative of our equation with respect to time. Now, the A part says find dy over dt, find this guy. If you tell me what x is, you tell me what y is, and you tell me what the change in x with respect to t is. We're just given 3 values that we can substitute into that equation. One other thing we could have done to that equation, just to make it a tiny bit simpler to plug numbers into, we could have divided both sides by 2. All right, just to make it a tiny bit simpler. And 0 divided by 2 is still 0. So when x is 3 and y is 4, does that satisfy this equation? 3 squared plus 4 squared is 25. Yeah, that's a point on that circle. And the rate of change in x is 8. Find the rate of change in y with respect to time. So I'm going to put a 3 in place of the x, an 8 in place of the dx over dt, a 4 in place of the y, and I'm solving for dy over dt. I can solve that equation for dy over dt. Subtract 24 from both sides. And divide both sides by 4. And I'll get dy over dt is -6. Let me show you what that means, looking at our circle. The ordered pair 3, 4 would be 3 and 4 would be right here. If this marble is moving around that circle in such a way that the change in x is positive is moving to the right. So the marble is going this way and x is getting bigger. 8, we don't know the units here. It might be centimeters per second. It could be miles per hour. We're not given units here, but let's say it's centimeters per second. When this marble is moving horizontally 8 centimeters per second, it's going down, because that's negative, it's going down 6 centimeters per second. Does that look right? As x gets bigger, my y gets smaller. All right, and pretty steeply right there. So as X is getting bigger at 8 centimeters per second, Y is getting smaller at 6 centimeters per second. The B part asks us to find dx over dt, find how X is changing when X is 4 and Y is 3. Again, the ordered pair 4, 3 does satisfy that equation. It is a point on that circle. It's when X is 4, Y is 3, it's this point right here. So I'm going to substitute 4 in place of the X. I'm looking for dx over dt. I'm going to put 3 in the place of Y and -2 in the place of dy over dt. And solve that for dx over dt. I'm going to add 6 to both sides and divide both sides by 4. I get dx over dt is 3/2. So when dy over dt is negative, the marble's going down. And right here, as the marble's going down, what's happening to my x's? The marble's right here going down. As I move in this direction on the circle. Well, it's getting bigger though. Yeah, it's getting bigger at a slower rate. All right. Let's keep talking about marbles for a minute. Do a couple more of these. Number 8 and number 10 both say a point or a marble is moving along the graph of the function at the rate given. I'm going to be given a dx over dt or a change in the horizontal distance. X is always a change in horizontal distance. Y is always a change in vertical distance when we're talking about graphs. So dx over dt is the rate of change in horizontal distance. Find the rate of change in vertical distance. Find dy over dt for the given values of X. Make sure you include units. Number 8 is y equals 1 over 1 plus x squared. I went ahead and graphed that for you so we can better imagine a marble rolling along that curve. And the change in horizontal distance with respect to time is dx over dt, and we're given that dx over dt is 6 inches per second. So this marble is going to roll uphill to some peak and then downhill, and it's rolling at some constant rate of 6 inches per second. We want to know how the height is changing at some particular time. Now, X is, we're going to find how fast Y is changing at -2 right here. How fast Y is changing when X is 0 right here, and how fast Y is changing when X is +2. We're going to find how fast Y is changing at those 3 points. So first we need to differentiate both sides of this equation with respect to t. The derivative of y with respect to t is just 1 dy over dt. The derivative of the right-hand side, you know what? I wish I had, since that numerator is a constant, I wish I had written that as y equals 1 plus x squared to the -1. Then I won't have to use the chain rule or the product rule. I'm sorry, then I wouldn't have to use the quotient rule or the product rule. I could just use the chain rule. So the derivative of that would be -1 Same old ugly to the -2 times the derivative of the ugly. And what's the derivative of the ugly? The ugly is 1 plus x. The derivative of 1 plus x is just 1, but since we're differentiating with respect to time, what do I also have to have? Oh darn, I copied it down wrong right there. Okay, you for what I had written, Riley was right, but I had it written wrong. So you were right the first time when you said the derivative of the ugly would be 2x. And because we're differentiating with respect to time, we have to have that dx over dt. And you may want to clean that up a little bit before you start plugging numbers into it. You could write that as dy over dt is -1. I'll go ahead and say -2x over 1 plus x squared times dx over dt. And all three parts, we're looking for dy over dt. Kind of lucked out there because the y was already on the side by itself. So we're only substituting numbers into this right-hand side. When x is 2, dy over dt would be -2 times -2 over 1 plus -2 squared. Anything else? What else is part of that derivative? Dx over dt, and we were given that dx over dt was 6. So I could say times 6. And what would that clean up to be? 24 is -2 times -2 times 6 is the 24. And in the denominator, 1 plus 4 is 5. 5 squared is 25. So the change in vertical distance with respect to t is positive. When x is -2, when x is -2, is that marble rolling uphill? Yeah, that's why dy over dt is positive. What's the units on that 24/25? So it's just inches, that's 24 over 25 inches. It's a rate of change, so it's inches per second. The change in x was given to us in inches per second, so the change in y will be inches per second. When x is 0, we would have dy over dt is -2 times 0 over 1 plus 0 squared times 6 in the place of dx over dt. What's that? That's just 0. And again, it's inches per second. But let's see if that makes sense in terms of the graph. At x equals 0, this marble is sitting at the peak. And at the exact minute or the exact second that that marble is at the top, how fast is it changing in height? It's not at all for that split second. That tangent line is horizontal right there. So the slope of that horizontal tangent line is 0. For that split second, the y is not changing at all. At -2, the slope of the tangent line was 24/25. Do you expect to get a positive answer or a negative answer when x equals +2? Because at the point where x equals +2, the marble is going to be going downhill. Can you tell me what you expect that slope to be without having to plug numbers into this formula? Yeah, this graph is symmetric with respect to the y-axis. So its speed is the same at -2 and +2, but its velocity is different because on one side it's going uphill, on the other side it's going downhill. So you can plug numbers into the formula to verify that, but I know I'm expecting dy over dt to be -24/25 inches per second. All right. Did I remove A and B? Yes, I didn't want to do all 3 parts. I just wanted to do one part to make sure that you could handle this very same thing with a trigonometric function. I didn't feel like we needed to do it 3 times. So the trigonometric function that we have graphed on number 10 is y equals cosine x. Remember cosine x, one period of cosine x, we usually say starts at 0, 1 and continues to back to 2 pi 1. This graph is just shown from, let's see, I don't know if that's I don't know what we're counting by there. I guess just centimeters. Yeah, we're counting by centimeters from -4 to +4. That doesn't make sense. That's not what I meant. The change, this is the graph of y equals cosine x. It's probably from, from -pi to +pi. And we don't have to figure that out, but it was bugging me, so I did. Differentiate both sides with respect to t, and we would have dy over dt equals what? That's the derivative of cosine x with respect to time. Negative sine x. And what else? Yeah, d of x over dt. We're differentiating with respect to time. Now, something I didn't think to say in number 8 was after we differentiated, and it's very important that I said after we differentiated, we can say, you know what, that dx over dt is a constant. That rate at which x is changing is a constant, 6 inches per second. I could have put the 6 in right here instead of substituting it in both places here. So I'm going to do that on number 10, just because I remembered. If dx over dt is 4, then I can put that constant 4 in the place of dx over dt here instead of having to do it in part A, B, and C. So dy over dt would be -4 sine x. And the 4 is coming from right there. So at x equals pi over 3, again, if I'm counting by, must be counting by pi over 3s. If that's 1/3 pi, 2/3 pi, and this is a whole pi. then at pi over 3, right here, do you expect your dy over dt to be positive or negative? Yeah. X is getting bigger, the marble is moving to the right, but y right here is getting smaller, and we want to find out how fast it's getting smaller. So dy over dt would be -4 sine of pi over 3. So what is sine of pi over 3? Where we get 3 over 2, it's where your y is almost 1. That would simplify to -2 square root of 3. And that's how fast the marble is going downhill. Downhill because dy over dt is negative. Hey, what should the units be there? Yeah, if x is measured in centimeter, dx over dt is measured in centimeters per second, then dy over dt is measured in centimeters per second as well. So far, so good? All right. All of those problems were just marbles rolling on some path defined by an equation. And we were given how fast one of the quantities was changing, the two quantities being horizontal distance and vertical distance. You tell me how fast one of those distances is changing. I can figure out how fast the other distance is changing. Yeah, it's a ratio. The rest of the problems aren't just marbles rolling around curves and the equation of the curve is given to us. We have to come up with an equation for how our quantities are related and how they both depend on time. So these 4 steps you need to use on every single word problem in section 3.7 or any related rates problem. It's all about using the correct symbols for the quantities being talked about. So step 1 is going to be identify all quantities that are given. Maybe the problem is air leaking out of a balloon, and we're going to be given how fast the radius is changing. We want to know how fast the volume is changing. The volume would depend on the radius, right? The smaller the balloon, the less air is in it. And both of those quantities depend on how long the air's been leaking out. So what symbol would we use for the change in radius with respect to time? With respect to time tells you this is a rate of change. It's not just going to be an R or a V or a T. All of our rates are going to be something over dt. So what symbol would be the change in radius with respect to time? dr over dt. What symbol would we use for a change in volume with respect to time? dv over dt. So we have to be given certain quantities and certain rates, and we need to label those correctly. Sketches are very helpful when it's something that you can draw. So make a sketch and label the quantities. Number 2, write an equation involving the variables whose rates of change are either given or to be determined. I have to have an equation that in the example of the air leaking out of a balloon, I need an equation that has a dr over dt in it and a dv over dt in it, because both of those things depend on time. After we get that equation, it's going to be like the ones we just did. We're going to differentiate with respect to time, remembering that Anytime we differentiate a quantity that's depending on time, we have to have that related rate symbol as part of the derivative. And lastly, after, and this is very important, after you differentiate, you can substitute in anything that's constant. Like here, dx over dt was constant. Here, dx over dt was constant. So you can substitute anything that is constant and solve for the required rate of change. Include units in your answer. Anytime that I tell you you need to memorize this, I'm giving you a heads up for being able to do this on the test without prompts. I was thinking on the way to school this morning about, you know, why some folks seem to understand a concept in class, but when they get home, or certainly when they get on a test, they can't do it. It's not because the math is, they're bad at math, it's because they're bad at words. They don't have the words they need to talk themselves through the process. So I'm giving you words that by the test, by the time we get to the test, you should be able to say, okay, what are my steps for solving related rates problems? One, identify the quantities that are given, the rates that are given. You figure out the symbols I need for the rate I'm looking for and draw a picture. That's step one. Step two is come up with that equation that relates the rates that I either know or I'm looking for. Step three, differentiate both sides with respect to time. And step four, now I'm ready to plug in. All right, you need to be able to say those to yourself so those words are there when it comes test time. Let's start with a simple one. Oh, it is a balloon. Ha, it's a balloon with air leaking out. No, it's a balloon with air being pumped into it. All right, so number 14, a spherical balloon is inflated with gas at the rate, let me get my highlighter here. The fact that that's a rate tells me that that's not just an R or a V, it's a rate, it's something over dt. And then I look at the units to determine what this is a rate of. Cubic centimeters is a measure of what quantity? That's volume. So what symbol will I use for a rate of change in volume? Yeah. I'm given that dV over dt is a constant 800. Find the rate of change in the radius means we're looking for what? What symbol would we use for rate of change in radius? Yeah, that's dr over dt. On dr over dt, and I could have left a longer blank there and said when r is 30 for that. Oh, I have it right here. When r, we're going to do the a and the b part. The a part is when r is 30 and the b part is when r is 85. So I don't need that right there. I have it below. All right, air is being pumped into this balloon at a constant rate. Here's the radius of the balloon. It's getting bigger. As the radius gets bigger, what happens to the volume? Volume of air in the balloon. It's getting bigger too. Or as the volume gets bigger, the radius gets bigger. Makes sense. All right. What is an equation for volume in terms of radius? Well, there are some formulas I expect you to know. Area of a rectangle, circumference of a circle, area of circumference, Yeah,
Because
area.
isn't a sphere basically the volume of a half circle times
How would you get the volume of a half circle? That's just volume of a half circle times 2 is volume of a whole circle. And so how do you find the volume of a circle?
I forgot all this formulas.
Right, right. Okay, the
Because
sentence I started and then forgot to finish was, there are certain formulas I expect you to know, but there are certain formulas you don't have to walk around with in your head at all times. I would give it to you if you needed it on a test. I happen to know, because I've used it for so long, that volume equals 4/3 pi r cubed. Any formula you need will be in it's either front or back cover of your book, or you can Google it. But on the test, I would give that to you. You don't have to memorize volume of a sphere.
So in certain cases, like this about stuff.
Well, we have to have the equation involving the variables whose rates we know or whose rates we are looking for. We have to have an equation that relates V and R. You don't have to have that memorized, but you do have to be able to differentiate it and then substitute numbers in. So what is the derivative of the left-hand side with respect to T? dV over dt. And what's the derivative of the right-hand side with respect to T? Would be good in that 13/3. Yeah, it's just 4 pi is a constant.
But
Oh, hold on for a second. 4 pi is a constant, so I'm not going to need the product rule. We all agree I'm not going to need the product rule, so all I need is the power rule. So what would the power rule give me? And then what would happen? No, what's 4/3 times 3?
oh, I see.
It's just the R that's cubed. So using the power rule, what's 3 times 4/3?
Well,
I'm still waiting on the answer to the question I asked, which is what is 4/3 times 3? It's just 4/3. Yeah, this is just 4 pi r squared. And what else? Once we're differentiating with respect to time, dr over dt. Are we all okay with why the derivative of 4 pi r cubed is 4 pi r squared? Okay. That was actually, I've written that too high. That was my step 3. Step 2 was write the equation. Step 3, differentiate both sides with respect to t. I have that. And what did we say was constant here? What's not changing in this problem? Well, of radius and volume and change in volume and change in radius, which one of those things is constant? The rate at which the air is being pumped into the balloon is constant. So if that's constant, I can say, actually, I think I'll put words in here. Since dV over dt is 800, we can just put the 800 in place of dV over dt. And what we're going to be solving for in the A part and the B part is the dr over dt. Do we have everything in the A and the B part? Do we have everything we need to find DR over DT? Yeah, and in the A part, we can put 30 in place of R and solve for DR DT or over DT. And in the B part, we can put 85 in place of R. Since we're gonna have an A part and a B part, we may wanna just solve this for DR over DT. Get that by itself before we plug numbers into it. Yeah, you don't have to, but since you're gonna have to do it twice anyway, I'd go ahead and divide both sides by 4 pi r squared. That would give you dr over dt is 200 over pi r squared. That'll be easier to plug in numbers for R. So in the A part, dr over dt is 200 over pi times 30 squared. And that's 200 over 900 or 2 over 9 pi. Squared is 900, and 200 over 900 just reduces to 2 9s. And pi is still in the denominator. So 2 over 9 pi. And what's the units on that change in R? Is radius measured in cubic something? It's just centimeters. If volume is cubic centimeters, then radius is just centimeters. So that would be centimeters per second. Oh, not second, it's minute. That's kind of important. All right, what about when R is 85? And the change in radius per second would be 200, not per second, per minute. 200 over pi times 85 squared. Yep, I don't have that answer written down. And can't do 85 squared in my head. I tell you what, just go ahead. Nah. So 200 over 7,000 what?
225.
And then I'm sure that will reduce by 25. The units on that will be centimeters per minute also. Now here's the big question, the make you squint question. The volume is changing at a constant rate, yes? Why isn't the radius changing at a constant rate? It's changing at different rates depending on what the radius is. Think about pouring water into a vase that is, let's say, wide at the bottom and gets skinnier. Think about pouring water into a vase that's wide at the bottom and skinny at the top. Is the rate of change in the height of the water going to be constant as you're pouring water into the vase? Where is the height, the depth going to be changing more slowly? At the bottom, because it has to fill up more Actually, yeah, more space. Yeah, it has to fill up more space. Once you get to the skinny end of the base, the water starts rising rapidly. This is the same thing. When that radius is just 30, like right here, the balloon's going to be filling up more quickly than when the radius is bigger, when the radius is 85 centimeters. So it's going to go, the radius is going to change rapidly and then slowly and then get rapid again as you get closer to the top. All right. How are we doing? 5 minutes. I think we can get 16 done. Let me check something. It's a pretty fast one. Yeah, you can write a sentence there. I'm not sure. I don't want to write a sentence down right now. Number 16. All edges of a cube are expanding at a constant rate of 6 centimeters per second. The fact that that's centimeters tells me it's a measure of what? That's just a length. That's the length of an edge. So we're going to call one of the edges X. And what will we use for that rate of change in X? That 6 is a rate. So it's not just going to be X is 6. It's going to be what? Yeah. That's dx over dt. So we're given that dx over dt is a constant 6 centimeters per second. Find how fast the surface area is changing. What symbol do you think we'll use for surface area? Rate of change. Absolutely, that works. If we let A be the area, then that's dA over dt times dA over dt when each edge is 10 centimeters. What symbol represents the length of each edge? That's just what X is. So when X equals 10. Do you see how we converted each phrase of that problem into its mathematical representation? And we use something over dt anytime we were talking about a rate. If we're just talking about a length, that's X. Now, which of these things is constant, the 6 or the 10? The 6 is constant. How fast the cube is expanding is constant. That 10 is just some particular moment in time. Can we come up with a formula for the surface area of this cube in terms of the length of one of its edges?
6 times X squared.
The area of one side would be, area of one, let's call it face, like it was a cube, a die. Then the area of one face is X times X is X squared. And the surface area, how many sides does that die have? Yeah. So an equation for surface area in terms of the length of one side would be A equals 6x squared. And that's a formula I would not give you because you can figure it out. All right, differentiate both sides with respect to t. The derivative of the left-hand side would be what? with respect to t. dA over dt was the derivative of the right-hand side with respect to t. Anything else?
Yeah, that.
dx over dt. Now, here's the problem with plugging in numbers too early. And that's the thing that I see on the test. If you went ahead and put 10 in the place of x right here, the right-hand side is just a constant, and the derivative of a constant is 0. So you can't plug in numbers for things that are changing until after you've done the differentiation. Now we can say when x is 10, dA over dt will be 12 times 10 times our constant dx over dt is 6. That's 120 times 6, or 720. And what are the units there? Think about what we're measuring. dA, that A stands for, the A stands for area, so that has to be centimeters squared per what? Yeah. It's not just centimeters, it's centimeters squared per second. All right. For tonight's homework, and I probably will take it up tomorrow. It's just 1 through 13 odd. This is the back page of, or the last page of the notes has the homework on it. You can label it that way if you want to. Day 1 is 1 through 13. Day 2 is just 4 problems, and day 3 is 4 problems. You know what makes it easier, I think, Raleigh, and no, I think you would be jinxing yourself to go, this is easy, because they're going to get increasingly difficult. But the thing that is seeming easier is the fact that you can picture something happening. You're almost doing an engineering problem now, and it's meaningful, where the chain rule with X's and Y's in it is not meaningful. You can't picture what's going on. Yeah. But now you see that you're changing those English words to those calculus and algebra symbols, and you start to realize why algebra was invented. Yeah, in calculus. It was so that you could use those symbols to answer questions, solve problems. All righty. Y'all have a good day. And again, I probably will take up 1 through 13 tomorrow.